Hi everyone, I hope that you had a great weekend today. And today, welcome to my lesson. We will learn about monotonic function and local extrema of function. Now, look at the board. I have a graph. I have two cases. In the first case, I will let x1 with the value fx1, x2 and its value fx2. We can see that x1 is less than x2, and then fx1 is less than fx2. In the second case, I have this x1 and its value fx1, x2 and its value fx2. So we can see that x1 is less than x2, but fx1 is greater than fx2. In two cases, we have the first case, the function is rise in the interval, and the function is falls in the interval. We call them the monotonic function, and we have definition 1. Suppose case is an interval or a closed interval or a half closed interval. And the function y equals fx is defined on K. The function is increasing if for all x1 less than x2, then fx1 is less than fx2, and the function is decreasing if for all x1 less than x2, but fx1 is greater than fx2. And beside using this definition, we can use one of the application of the derivatives to conclude this by using derivative. Now look at the graph. At each point in the interval from A to B. If we take a point, then we draw the tangent line. You can see that the gradient of the tangent line, the tangent line slopes upward. Then the gradient of the tangent line, or the derivative of function, is greater than 0. And at each point in this, we will draw the tangent line. And you can see this, the tangent line slopes downward, so that the gradient of the tangent is negative, or derivative is less than 0. So we have the definition 2. Given the function y equal fx has derivative f prime of x for all x belong to k. So if f prime of x is greater than 0 for all x belong to k, then the function is increasing. Okay, and if f prime of x is less than 0 for all x belong to k, then the function is decreasing. And we generally call increasing or decreasing is monotonic function. So we can see that to find the monotonic function of the function, we will follow 4 steps. We can see that it has been proven that if f prime of x is greater than or equals to 0, or f prime of x is less than or equal to 0, and for all x belong to k, and f prime of x equals 0 at only finite many points on k, then the function is increasing or decreasing on k. And if f prime of x equals 0 for all x belong to k, then the function is constant on the interval k. And to do this, we will follow 4 steps to conclude the monotonic function. Step 1. We will find the domain of the function. Okay. Number 2, we will calculate the derivative f prime of x and then solve the equation x prime of x equals 0, or find where the function is undefined. Okay, and step 3. In step 3, we will construct the table of variation. This table have 3 rows. Row 1 for x, row 2 for the derivative, and row 3 for the function f(x). And in the first row for x, we will take x from step 2 to the row 1 and then order the x value increase from left to right. Order the x value on step 2 to the first row. Increase from left to right, and then we find the sign at the right hand has the same sign of the leading coefficient. After that, we will change sign if x passed through the simple root or the odd multiplicity root, and we doesn't change sign if x passed through the double root or the even multiplicity root. And the fourth step is conclude the monotonic function. And follow 4 steps, we have 2 examples to find the intervals that the function increasing or decreasing. We have example 1. The function y equal fx equal x cubed plus 3x squared plus 2. Yes. Follow 4 steps. We will start the first step. The domain of the function is real. The derivative f prime of x equal 3 times 2 squared plus 6 times x. And f prime of x equals 0 if and only if 3 times x squared plus 6 times x equals 2. If and only if x equals 0 or x equals negative 2. Yes, and in step 3 we will construct the table. Three rows. Row 1 for x, and we will start from negative infinitely to negative 2, 0, and infinitely. Row 4 for derivative. It equals 0 at 2 points and fx. So, to find the first sign in the right hand, we will focus on the leading of coefficient is 3, and 3 is greater than 0, so the sign is positive, and as 0 and negative 2 are simple root, so we change sign negative and positive. In the third row, we will represent the monotonic function by using the arrow up and down, up and down. Okay, and we will conclude that the function is increasing in the intervals negative infinitely to negative 2 and 0 to infinitely. We must to remember this. We will use the semicolon or the word and. Here, we happen to we don't use word or remember this, don't use or the symbol union in this case, and the function is decreasing in the interval negative 2 to 0. And example 2. Y equal fx equal x minus 2 over x plus 1. The first step, we will find the domain of the function of the function equal real except to -1. The derivative f prime of x equals, we can use the fast formula ax plus b over cx plus d, and if we want to find the derivative of x, we use this formula a multiplied d minus b times c over cn plus d all of this squared, and we have the result 1 minus -2 equal 3 over x plus 1 squared, and we can see that it always greater than 0 for all x different from -1. We take this, and in the step 3, f prime of x f x. In step 2, we don't have we can solve this equation, but in step 1, we will see that the function is undefined at -1. So we put this into the table. Undefined, and the sign is always positive. So we use 2 arrows to represent this, and we conclude that the function is increasing on the intervals -infinity to -1 and -1 to infinity. Okay, this is the first one about the monotonic function, and we will go to part 2 about local extrema of function. Come back to the graph. We can see this. In this case, f prime of x is greater than 0. I will say it at a x0 b x0, sorry, x0 and b. Okay, f prime of x is greater than 0 for all x belong to a x0, and f prime of x is less than 0 for all x belong to x0b. Then we will say that x0 is a local maximum of the function x0. x0 is a local maximum, and f x0 is for the local maximum value, and this one x0, f x0 is a local maximum point of the graph of function. And in this case, if f prime of x is less than 0, and then is greater is greater than 0. Now, look at this. Okay. Then we will call this is the local minimum of the function. And this point is called the local minimum of the graph of function. Okay. We will have the definition about this. Given the function y equals fx continuous on the interval a to b, and x0 belongs to the interval a to b. If f prime of x is greater than 0 for all x belong to a x0, and f prime of x is less than 0 for all x belong to x0 b, then the function has a local maximum. In this case, x0 equals a local maximum of the function, maximum point, and fx0 is called a local maximum value of the function. x0 semicolon fx0 is the local maximum point of the graph of the function. Remember this. This one is of the function, but this one is the graph of the function. Okay, if f prime of x is less than for all x belong to the interval a x0, and f prime of x is greater than 0 for all x belong to x0 b, then the function has a local minimum. In this case, we call this x0 is a local minimum point of the function. fx0 is a local minimum value, and x0 semicolon fx0 is a local minimum point of the graph of the function. And to find the we can call generally they are local extrema of function. Instead of we call the local minimum or local maximum, we can call the local extrema of function. And to find the local extrema of function, we will follow 4 steps like this one. But in the step 4, instead of we conclude the monotonic function, we change this step to conclude the local extrema of the function. And come back to 2 exercise. 2 example. In the 4th step, we will change this. Okay. If the derivative change sign from positive to negative or negative to positive when x passes through x0, we will call it a local extrema of the function. So, to find this, we will use the calculator. We will find at x equals -2, fx equals 6. And this one, we have the value 2. We will find the limit of fx when x approaches to the negative infinite is negative infinitely, and when x approaches to infinitely, we will find the result is infinitely, and we will conclude that the function has a local maximum at x equals -2 and f of -2 equals 6. The function has a local minimum at x equals 0 and f 0 equal 2. But in this example, we can see that the derivative don't change the sign. This one is positive and this one is positive too. So we can look at this. It's don't change sign. So we have the conclusion. The function has a local extrema. Okay, this is our lesson today, and I hope that you will understand what I said. And I want you to give me some comments in this video. Thank you for watching.